Alright guys, welcome to Roots and Radical Expressions. This is the first lesson in a new unit. And today we're going to be looking at this essential understanding. Really corresponding to every power there is a root. For example, just as there are squares, second powers, there are square roots. And just as there are cubes, third powers, there are cube roots. And so on. Fourth powers, they have fourth roots. Fifth powers, fifth roots. Okay, so what is an nth root? For any real number a and b and a positive integer n, if a to the n equals b, then we say that a is the nth root of b. So these are two big ideas that we're going to be exploring today. Okay, so for example, 3 to the fourth equals 81. What we would say is that 3 is the fourth root of 81, and that's that nth root definition. Okay, and since 3 is positive, we call that the principal root. Now the principal root is very important. On your graphing calculator, when you take the square root of 81, it only gives you 9 instead of -9, and that's because of this, the principal root. It's the positive root. Okay, and that's how your calculator is set up to handle square roots. Okay, just as a review, we have the radical sign here. Okay, the index is called n, that's whatever root you're taking, cube root, square root. If it's a square root, you won't see it there. Okay, and underneath the radical sign, the radical symbol, is what we call the radicand. In this case, the radicand would be 81. So here's three things we need to talk about. The square root of 25 on your calculator would give you 5. The square root of 25 indicates the principal root of 25. Okay, there's nothing up front. Here we almost say we want the negative root, or the opposite of the principal root. So the opposite of the square root of 25 is -5. These numbers should be opposites. So -25 is the opposite of the principal root. And lastly, this got erased, we have plus or minus when they're going to ask for both the positive and the negative root. The positive root would be the principal root, the negative root is just the negative root. Plus or minus the square root of 25 is plus or minus 5. Plus or minus the square root of 25 does indicate they want both square roots. Now, in this case, in this last part, suppose n is an integer greater than 1 and a is real. So a can be, if a is a real number, it can be greater than 0, less than 0, or equal to 0. And this tells you what happens. If a is greater than 0 and we have an even power, we have one unique positive root and one unique negative root. For example, the square root of 81 is plus or minus 9. That's what this thing indicates. If you have a positive number and n is an even power, you're going to have two results, a positive and a negative real root. If a is less than 0, there's going to be no real roots here. And for example, the square root of -25, that's not a real number. There's no real roots there. They have imaginary roots, plus or minus 5, but they're not real. And if a equals 0, the one real root is 0. If we go on to the odd powers, if a is a positive number, positive real number, we get one unique positive root. If a is negative, we get one negative root. For example, the cube root of -8 is -2. And that's an example where you have an a value less than 0 and a n value, the index, being odd. Okay? Again, if a is 0 and you have an odd power, you still get 0 as your root. Alright, so a couple of examples. What are the cube roots of 0.008, -1000, and 127? So 8 thousandths here is equal to 0.2 cubed. So we would say that 0.2 is the only cube root of this problem because a is greater than 0, okay, and the index is odd. -1000 is equal to -10 cubed, so we'd say -10 is the only cube root of -1000, and we have 1/27 as our last example. 1/3 cubed gives us 1/27, so 1/3 is the only cube root of 1/27. And that goes back to helping us out with the last slide, the previous slide there, and when you have an a value and an n value, you can see what types of solutions you can have and what types of roots you can have. Part B is really the same thing. What are the fourth roots of -0.0001 and 16/81? Well, this first one's not possible because you have a negative a value and you're looking at an even power. So this is not possible. There's no real roots there. 16 over 81, these are both actually perfect squares. 2 to the 4th is 16 and 3 to the 4th is 81. So 2/3 to the 4th power works. But remember, this is a positive number and an even root, an even index. So that means there's a plus and minus. And there they are, plus and minus, 2/3. Those are the roots. And this example just goes back and kind of reiterates that last slide. Okay. Let's get a little more complicated. We're going to simplify. And again, you've seen this in algebra. And what we're going to do is try to see whatever our index is, we want to write all the numbers under there, the terms, to that power if possible. So first we're looking for plus or minus the square root of 16y to the 4th. That's a square root. Well, 4 squared is 16, and we can rewrite y as y squared squared. And so when we simplify this, we have plus or minus 4y squared, because we can rewrite y to the 4th as y squared being raised to the 2nd power. Okay, and that base comes out. Part B, the negative square root of x squared minus 6 to the 8th power. 8 can be broken down into 4 times 2. And we have an index of 2 because it's not written. So we have the quantity x squared minus 6 being raised to the 4th power, raised to the 2nd power. So guess what? That base, x squared minus 6 to the 4th power, comes out, and it's the opposite. We want the negative. Same thing in part C. The square, or the 5th root, of 243, a to the 20th, b to the 25th. The index is 5. Look at 20. Look at 25. 20 is 5 times 4. 25 is 5 times 5. And 243 can be written as 3 to the 5th power. So I've rewritten all that here. All these can be written, okay, to the 5th power. So 3, a to the 4th, b to the 5th, all raised to that 5th power, because 3 to the 5th is 243. A power to a power, you multiply. 4 times 5 is 20. 5 times 5 is 25, and there's our 5th root. 3a to the 4th, b to the 5 is the 5th root. Lastly, you have another square root, but you have a negative 16 in there, so hopefully you're saying hold the phone. There's no real roots. You can't take the square root of a negative number. It doesn't mean you couldn't simplify this, though. We know that 4 squared is 16, so you get that plus or minus 4i. X to the 4th is x squared squared, so the x squared comes out, and y to the 8th is y to the 4th squared, and we get y to the 4th coming out. The last slide here is very important, and it deals with what happens when you find an even root of an even power, and the result is an odd power. You have to use absolute value of the result to ensure the power is non-negative. So here's what it comes down to. Let's look at an example. So we have an index that's even, an even root of an even power. Okay, so we have even, so 8 and 12, those are even numbers. And the result becomes an odd power. You have to take the absolute value. So let's look. We need to write these as powers of 4 if we can. Well, 8 is 4 times 2, so look, x squared to the 4th power. The 4 would be on the outside, so they cancel. 12 is 3 times 4. Okay, so y cubed to the 4th power. And so this is what they mean. Even power, okay, or excuse me, even root, even power, but what comes out would be a cube, and I missed that cube there. An odd power comes out, so you have to put in absolute value, and that's what this says. This is a very important rule. Let's look at another one. Square root of 36y to the 6. Even root, even power. 36 can be written as 6 squared. Y to the 6 is y cubed squared. So look, there's an even power, even root, even power, odd power coming out, so you have to put that in absolute value. And finally, the last one, the 6th root of 64 times the quantity x squared minus 3 to the 18th power. Even power, even root. And we can rewrite 18 as raised to the 3rd power, and that 3 times 6, right? So you can take x squared minus 3, that base, raised to the 3rd power, and that whole thing raised to the 6th power. And look what comes out. You have an even number to an even root, and we have an odd power coming out, so you got to put that in absolute value. So that is an introduction to radicals. If you guys have any questions or comments, you can type them below or email me at nicholas.bennett@dc.gov.